Hey guys, and welcome to Chem Squad Chemistry. This is Mr. Mullins on the sticks today. We are going to be doing a little bit of everything. First off, starting with electron configuration in the shorthand. I know that in the other videos, you guys have learned to do the full out electron configuration, showing where all electrons are located on what energy level, on what sublevel, and how many there are on each sublevel. Today I'm going to show you a little shortcut. Something that you're going to need is a periodic table, as well as some space to write. So let's go ahead and get started. Oftentimes you are given an element, something like, say, bromine, which is pretty far down the periodic table, and if you've not noticed, the electron configuration gets very repetitive. So there is a shorthand way to drawing the configuration for bromine, but first let's go ahead and show you the regular way. Remember that Aufbau's principle tells us that you must always fill up the lower energy levels and sublevels with electrons before you are able to move on to the higher energy levels. So as always, we are going to be starting at energy level 1, sublevel S. And if you count, you have hydrogen and helium there to fill up that S sublevel, giving us the 2 of the exponent. Now that energy level 1 is done, we can move on to energy level 2, S, because S is the lowest energy sublevel, and we have lithium and beryllium there to give us our 2 electrons. Energy level 2 is not done, however. We need to account for the 2 P's. Moving over to boron, there are 6 atoms there: boron, carbon, nitrogen, oxygen, fluorine, and neon, which gives us our total of 6 electrons. Now that energy level 2 is complete, we can move to energy level 3, sublevel S. And as you see the pattern here, we have the 2 that goes along with it for sodium and magnesium. Let's go ahead and finish out energy level 3 by writing 3p6. That takes care of aluminum through argon. We can move on down to energy level 4s2, which gives us potassium and calcium. Now remember, when we go into the D sublevel, they are actually a lower energy level, where we have Sc that drops down to energy level 3. So we have the 3d10 that takes care of us all the way over to zinc. When we go back into the P sublevel, it bumps back up to 4p, and we just need to count over to bromine, which happens to be 5 atoms away. So this is the long version of the electron configuration for bromine, but there is a shorthand version. The rule of thumb that's going to go along with this is that whenever you are doing the shorthand version, you need to find the most recent noble gas, and you are allowed to start there. Now, recent means behind you, not in front of you, so you're not allowed to go to the noble gas in front of bromine in this example. You're allowed to go to the one behind it. So instead of going all the way back and starting at hydrogen, we are going to go backwards from bromine all the way back until we get to a noble gas, which, remember, is in group 8. And it looks like in this situation it is going to be argon. So argon is number 18. It is behind bromine, the most recent noble gas. You should put argon in brackets. This is showing us, signifying to other people that, hey, I'm going to be starting with argon on this electron configuration, not all the way back at energy level 1 like we did up here. So after we start at argon, we just continue on from there like nothing has changed. After argon, we're going to be going down to potassium, which is on energy level 4, sublevel S, and we count potassium and calcium, that's 2. After that, we move on over to the 3d10, that takes care of us through zinc, and then we bump back up to the 4p5. So nothing is different here except for the argon, which is telling us where we start. We notice that this is the same in the shorthand as it was at the end of our long version, showing us that we did something correctly. The argon is simply replacing the version of the beginning of the long version. Let's try another one. Let's go ahead and do it for phosphorus. So phosphorus, we need to find the most recent noble gas. Phosphorus is number 15. We're going to go backwards, and we see that neon is the most recent noble gas, and that's where we'll start. After neon, we go down to sodium, which is on energy level 3. That's S, and we count sodium and magnesium. And we can move on over to the 3 P's, and we count aluminum, silicon, and then there's phosphorus, so it'll be 3P3. You see that shorthand helps us to do these a little bit faster, but it also gives us just as much information. You notice that the valence electrons are still here for us to count. Now that we've talked about doing the shorthand for all of the electron configurations, there's one more thing that you may need to take into consideration. You already know that fluorine all by itself is not a stable atom. Reason being, it only has 7 valence electrons. It is in group 7. So typically we're not going to find fluorine all by itself. It's going to create a bond with some other atom in order to become stable. Fluorine, as you may know, typically has an oxidation number of -1, which means to us that fluorine has gained an electron in order to become stable. Sometimes you're going to be asked to draw the electron configuration for these ions. Now you have to take this into consideration. This -1 means that you've gained an electron. So fluorine is no longer acting like fluorine, it's acting like its neighbor neon, who has 8 valence electrons. So instead of drawing the configuration for the fluorine, we're actually going to be drawing it for neon, because that shows us fluorine has gained that 1 extra electron and has become stable. So let's go ahead and give that a try. So for fluorine -1, the anion, non-metal, we're always going to start at 1s2. That's Aufbau's rule. We must fill electrons at the lowest energy level before we can the upper level. Moving on from 1s2, we have 2s2. Then we move over to 2p. Now typically you would write 2p5 here, but because fluorine has this -1, it tells us it's gained an electron, so this is actually 2p6. And if you were to draw the electron for configuration for neon, you would see that it is the exact same thing, and that's because fluorine here is acting like neon. It's trying to be stable. It's showing that it has a full valence shell, just like neon. If you have any more questions about these, make sure that you are practicing them, because they are the basis of this 3-step problem that we are going to be covering very soon. All right, now that we have our electron configuration taken care of, we are going to move on to the second step of locating these electrons. Eventually, we're going to try to do some things with the quantum mechanical model to show us exactly where these electrons are, getting more and more specific, not only knowing their energy level and sublevel, but also knowing more about the electrons themselves and their location. The next step in this is called the orbital notation, step 2, if you will, step 2, first of which being electron configuration, step 2 being orbital notation. Here we have Hund's rule. Hund was a scientist that was working at the same time trying to describe where these electrons are, and he did so with more of a visual representation. Now these, the words, this is the definition, they may seem a little confusing, but I have a little example to explain it to you here in just a second. It says, every orbital in a subshell is singly occupied with 1 electron before any orbitals are doubly occupied. Now what that means is that when you have all of these different orbitals, all of these different locations where the electrons can be, they are going to singly occupy, meaning 1 electron will be put into each orbital before any of them are ever full. Now the reason this happens is because electrons, as you know, are negative entities, right? And we know that if you put 2 negative electrons near each other, they are going to repel one another. They're going to try to be as far apart as they possibly can, until they're forced to be side by side. And this next little part of Hund's rule down here explains what will happen if we put them side by side. It says all electrons have the same spin in these singly occupied orbitals. If they're all by themselves singly occupied, they will all have the same spin. If they are forced to be put close together, if they're doubled up in the same orbital, they are going to spin in opposite directions. And we refer to that as a positive spin, which would be up, or a negative spin, which would be down. So we're going to have a little more examples and a few more times to talk about that. But you do need to know what Hund's rule says. It's also known as Hund's rule is also known as the bus seat rule, and I'm going to show you why that happens. So let's imagine that, here's our little bus. We're looking down on the bus from above. Here's the door to get on, and you have all of these seats. You get on the bus in the morning, and here's you around here, y'all happy-go-lucky, coming to school, ready to learn some chemistry. Got your little long hair, and you get on the bus. You immediately get on a seat, right? You're the only one on the bus. You're going to be sitting all by yourself. Electrons are the same way. If they are alone, there's only one of them. They're going to be on an empty orbital. Now let's imagine that you're sitting here, and another person gets on the bus. Here's your buddy, got on a ball cap. Most of the time in the morning we don't get along, so do you think he's going to sit beside you? No, he's going to find his own bus seat. And eventually people are going to be occupying one person in every single seat, right? No one is doubly occupying a seat. We are singularly occupying these seats. Electrons are the same way. They will singularly occupy an orbital instead of doubly occupying it. Eventually there's going to be no more seats that a person can sit in. So here comes your new friend's going to come along, and they're going to get on, and they're going to have to sit with someone, right? They're going to get in the bus seat with one of those other people. Same thing happens with electrons. If all of the orbitals are singularly occupied, the electrons have no choice. They're forced to be together. And when that happens, because of the like charges getting close to one another, these electrons start to spin in opposite directions. And we're going to show how this happens with a diagram that we call an orbital diagram. So let's go ahead and practice one of these orbital diagrams. Before we can do an orbital diagram, you guessed it, this is step 2. We have to first draw an electron configuration. So we're going to do an easy one to get started with. Let's go ahead and together draw the electron configuration for nitrogen. So I'm just going to title it EF, for electron configuration for nitrogen. We know that it starts at the sublevel and energy level 1s2, followed by 2s2, and eventually we get to 2p3. You should be able to find that on your periodic table. You should also know how to do it. I'm going to assume from this point forward everyone is comfortable with electron configuration. The next thing we're going to do is orbital notation, which is going to show us where these electrons are going to be on their orbitals. So just a little review. You should remember that the S, the P, the D, and the F are all different sizes, right? The S is the smallest, and the F is the largest. You should know that 2 electrons are able to fit on one orbital, which shows me that the S has one orbital only because there's only 2 electrons there. The P will have 3 orbitals, the D will have 5 orbitals, and the F will have 7 orbitals. You can see that the F is the largest. If you can't remember these, then you can just think to yourself, oh, I know the S has 2 electrons because that's all that's shown on the periodic table. 2 electrons fit on one orbital. We are going to denote an orbital with a dash above the sublevel. So in this case, S has 1 orbital, we're going to draw a dash above it. The P has 3 orbitals, it's going to have 3 dashes. These are our locations that the electrons can exist. The D has 5, and the F has 7. You can see that the F is actually a very large sublevel. Denotes that, the flower that you've drawn, the shape of the F sublevel. So these are going to come into play while we're drawing our orbital notation. So we're just going to take our 1s, our 2s, and our 2p, we're going to redraw that. And you ask yourself, how many orbitals does an S have? Hopefully you just got it from over here. It has 1, so we're going to draw 1 dash. Here we have another S. It's going to have 1 sublevel as well. 1 orbital as well. Here we have a P, which is going to have a total of 3 sublevels. Now keep in mind we have to use Aufbau's rule at the same time as using Hund's rule. Just because we learned a new one doesn't mean the other goes away. Aufbau tells us that electrons fill the lowest energy level before it will fill any higher energy levels. So we take a look, and it looks like on the first 1s level we have 2 electrons. Remember, Hund tells us that electrons will spin up before they ever spin down. So we have 1 spinning up, 1 spinning down. They both go on the same line or orbital. We may even call them bus seats to help you with our little analogy. We look at the 2s. We have one electron that's going to spin up. I'm going to draw half arrows to save some time. And this is an up arrow. The second electron has nowhere else to go, so it is going to spin down with that electron. Here we get over to the 2p3. We notice that there are 3 electrons. We do not want them to go together. Remember, this is Hund's rule, so we're going to put one going up in the first orbital, another going up in the second orbital, and our third going up in the third orbital. Now you notice this is just like the bus seat. You get on the bus, you sit all by yourself until you're forced to sit with someone else. Also, Hund's rule tells us that they're all going to be spinning the same way unless they're forced to spin the other way. So this is my orbital notation for nitrogen. It tells us the energy level of every electron, the sublevel of every electron, the orbital of every electron, and the spin of every electron. So I could ask you, which will be our third step, what is this electron doing? You could tell me it's on the second energy level, the p sublevel, it's on this orbital, and it looks like it's spinning up. So there's lots of information to be had in this single orbital notation. Why don't we try to do another one? All right, for our second example, we are going to use fluorine. As you may know, fluorine is a non-metal. It's found in group 7. We expect it to have 7 valence electrons. It likes to gain an electron in order to become stable. It is an anion when it becomes an ion. You need to start becoming familiar with these words. So I'm going to assume we are good at drawing electron configuration. So I'm going to go ahead and draw out. You can see even I mess up. I'm going to go ahead and draw out our electron configuration for fluorine. The next thing we're going to do is start to draw our orbital notation. We have our 1s, our 2s, and our 2p, very similar to our last example. The s has 1 orbital, something you must memorize. This s has 1 orbital, and the p, who remembers it, has 3 orbitals, 3 locations for electrons. We look here, we have a 2. That tells us that there are 2 on the 1s. Remember, the first one's going to spin up. The next electron has no other seat to sit in, no other orbital to go on, so it must spin down. You notice how we're filling them in from left to right, from lowest to highest energy, just like Alpha wanted. On the 2s, we have 2 electrons, 1 spinning up. Again, nowhere else to go, so the next one will be spinning down. With the 5p, we are going to place 5. Remember, Hund's rule says these electrons will be all by themselves in these orbitals unless they're forced to be together. Now we notice we've run out of places to put them alone, but we have 2 electrons left up here, so they have to go somewhere. They're going to go in the first available bus seats, but they are going to be spinning down or negatively. So here is our next example for orbital notation for fluorine. Let's do one more that's slightly harder. Chromium will be our next example. So you notice that chromium is found in the D block. It is number 24. Please find it on your periodic table now. Chromium right beside manganese at number 24. So let's go ahead and write our electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Don't forget, when we go to the D block, we drop down in energy to 3d, and we count over to chromium, which will be 3d4. So there is our electron configuration. Obviously, our orbital notation is going to be a little larger. We're going to take our 1s, our 2s, our 2p, our 3s, our 3p, our 4s, and our 3d. Leave you a little space for the d because you should know that it is larger. Remember that s has 1 orbital, this s has 1 orbital, this p has 3 orbitals, this s has 1 orbital, p has 3 orbitals, s has 1 orbital, and d has 5. So now that we've had our orbitals drawn, you may be starting to realize that this is a pattern. As Alf said, the only way that I can put electrons on this high sublevel and this high energy level is to first fill up all of the other ones. So you can go ahead and fill them all in up to the 3D, or we'll take our time and do it together. We have the 2 electrons. Remember, one's going to spin up, one's going to spin down. That's showing us some of Hund's rule. The 2s, one's going to spin up, one's going to spin down. The 2p6, 6 electrons. Go ahead and practice it this way. All of them are going to spin up, before any of them spin down. Just get used to practicing that way and you'll never forget. The 3s, one's going to be spinning up, the other's going to be spinning down. 3p, it's going to have 6, so 3 up, 3 down. Notice how I did it. The 4s is going to have 1 up and 1 down. We finally get to our last energy level, which is the 3d4, and has 4 valence electrons. So you might be wondering where we're going to put them. Remember, they're going to take the first available bus seats. They're all going to be spinning up because that is Hund's rule. None of them are going to be sitting together. They like to repel one another. So now we have chromium, which shows us that there are 4 electrons out here on this 3D. They're all in their own orbitals. They are on the D sublevel in the 3rd energy level. So you get a lot of information from just a small visual diagram. Now you may be wondering, why is this diagram so important? Why is it that we are... Sorry about that. You may be wondering, why is it that we're drawing these huge diagrams, right? And that's perfectly fine for you to be thinking. But our final purpose and what we finally made it to are these things called quantum numbers. And what they do, they're kind of like a set of coordinates. Like if you said, hey, I live in Virginia, you could look up on Google Maps or Google Earth exactly those coordinates, like north longitude, west latitude, whatever it is, in order to pinpoint you using a series of numbers. So that's exactly what we're going to be doing here. We are going to use a series of numbers to describe where each electron is located and exactly what it's doing at that place. There are 4 numbers, and we are going to draw them in brackets, just like this. There's going to be 4 numbers here, and we need to know what each number stands for. This is something you must memorize, and you're going to notice that it gets more and more and more specific. Before I write them down, I'm going to draw a quick orbital notation for oxygen so that we can talk about it as we go along. So we know it's the 1s, the 2s, the 2p, 1, 2, 3 orbitals, 1, following Hund's rule and Aufbau's rule. We know that oxygen has 4 valence, 4 electrons on that p sublevel. So let's go ahead and draw the quantum numbers for specifically, let's go with this electron here. This electron right here, the one that has an arrow pointing down on the 2nd energy level, on the p sublevel, on this little orbital over here. So we're going to draw the quantum numbers for that. The first quantum number, the very first one, the one that goes here, is the energy level. And as you may recall, there are only 7 energy levels, so this is going to be a number between 1 and 7. It's a very simple way for us to know what the energy level is because we've already told ourselves when we drew the orbital notation. We noticed that the electron we are looking for is found on where? The 2nd energy level. So you guessed it, our first quantum number that we're going to draw is going to be a 2. Now I know that's a very general thing. We have canceled out these. We know that we're not talking about those 2 electrons. It must be one of these. But as you know, that's not specific enough. So the next number is going to get even more specific. The second quantum number is going to be the sublevel. And as you may remember, there are 4 sublevels, right? S, P, D, and F. The 4 sublevels, but sublevels S, P, D, and F are not numbers, so we're going to assign them a number, starting with 0. If you want to talk about the S sublevel, use a 0, the P will use a 1, the D will use a 2, and the F will use a 3. In this situation, it looks like our electron is on the p sublevel, so our second quantum number is going to be a 1. So now we've gotten more specific. We know that it is not these electrons because that's on the s sublevel. We now know that it must be one of these 4 electrons over here. The third quantum number is the third thing we learned about, our orbitals. Right? And to do an orbital, we're going to create a number line. This seems to be where a lot of confusion comes into play, but we'll take our time and describe it up here in the top corner. If we have, let's start with the D sublevel, we know that it has 5 orbitals. We are simply going to turn these orbitals into a number line. At the center of every number line you've ever dealt with is always a 0. So we're going to assign that center orbital a 0. The orbital to the right is going to be a +1. Even further right is going to be a +2. Can you guess what's below 0? It's a -1 and a -2. Now we know that, not all orbitals are that big. That specifically works for the D sublevel. Imagine if we had the P sublevel. We know that there are only 3 orbitals in the P sublevel, so we would put a 0 in the center, a +1, -1. If you're talking about the S sublevel, there's just going to be 1, so we're going to make it a 0. The F sublevel has 7 blanks, so it would go from -3 to 0 to +3. So there would be 7 numbers there for you to choose from. Now, this situation, we have a, looks like a P sublevel. So there are 3 locations. We're going to put a 0 under the middle one, a +1 on the right to the right, a -1 to the one on the left. We notice that our electron is found on the -1 orbital. So our third quantum number is going to be -1. It's important that you write the negative because that's different than +1. Lastly, our last quantum number is probably the easiest one to determine, and that is the spin of the electron. Basically, is it spinning up or is it spinning down, right? In this situation, we see that it is spinning down over here. So we are going to say it's spinning down. Now that's not a number, so we're going to make up a number for it. In this situation, if it's spinning up, we're going to call it a +1/2, and if it's spinning down, we're going to call it a -1/2. So our fourth quantum number is a -1/2. It seems like a lot of work. It isn't easy, but it does become very repetitive. And the more you practice it and the more work you're willing to put in, the better off you will be. Now, it does take some practice, so don't get bummed out if you're not able to get it your first time. I'm going to do a couple practice problems. Sorry, I accidentally minimized the screen, but I'm going to do a couple practice problems with you, and from there you should be fine, so don't worry about it. Let's go ahead and do one more. So if you would, quickly write down the electron configuration for, let's go with magnesium. I'll give you a couple seconds to write that down. If you could please pause the video and write it down yourself, that would be great. I'm going to go ahead and start writing it. We have the 1s2, 2s2, 2p6, 3s2. Hopefully you can check yourself and know that you're right. If you were correct, go ahead and draw the orbital notation for this, the full orbital notation. Pause the video right now and draw the full orbital notation on your own paper. I'm going to go ahead and draw it. We have the 1s, the 2s, the 2p, and the 3s. We know the 1s has 1 orbital, the 2s has 1, the 2p has 3, and the 3s has 1. Now I'm going to ask you, just like most questions ask you, I want to know the quantum numbers for the last electron added. For the last electron added. So whatever electron we draw at the very end, by following Hund's rule, is the one I want the quantum numbers for. So let's go ahead and try that. We have the 2 electrons on the 1s shown here. So we put them up and then down. The 2 shown here, they're going to go up and down as well. 6, that's up, 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 down, down, down. And then finally we have the 2, which is, boom, there's my last electron added. It was the very last one I drew following Hund's rule. I'm going to change the color of it just so we can keep up with it. It is this pink electron here that seems to be spinning with a down arrow. It is found on the 3rd energy level at the S sublevel on this orbital here with a down negative spin. So as you notice, you basically know these quantum numbers because they're getting more and more specific, starting with the energy level to the sublevel to the orbital, and then finally we get to tell the spin. So if you ever forget what order they're in, Just think, we're getting more and more and more specific. So let's go ahead and start out with our first energy level. We are looking for the energy level, or our first quantum number. It's going to be the energy level. So in brackets, we typically write them in brackets. It's not mandatory, but that's how you'll see it most of the time. We see that this electron is found on energy level 3. We look for the next sublevel. We see that it is found on sublevel S, which we see right here. We're going to use a 0 for, so our second quantum number is 0. Our orbitals, we need to create a number line for our third, but because there's only one line here, we put a 0 there, so our third quantum number is also a 0. And lastly, the spin of our electron looks like it is spinning in the down direction, which we associate with a negative 1/2. And again, there are your 4 quantum numbers. They're pretty simple to do if you have your orbital notation down great. Now, something to think about is, oftentimes people have a misconception about electrons. They think that they're so tiny that they are, negligible. Well, that's not true. There's actually this guy named Pauli. He has this principle. It's called the Pauli exclusion principle. The Pauli exclusion principle, as you see written here, has to do with the location of electrons. Like I said, we think that electrons are so tiny they're negligible, but that's not true. Pauli came out and told us that no 2 electrons in one atom can ever have the same quantum numbers. What that tells me is that these electrons can never be in the same place at the exact same time. It's just impossible. Now, that's not to say that as one electron moves, another one may take its spot. That's possible, but not for them to be in the exact same place at the exact same time. So if I were to ask you to write the quantum numbers for every atom in the element that we just did, you would never have the same 4 quantum numbers. They're always going to be different. He also says that there are only 2 electrons can fit in one orbital, and when they fit in that orbital, they spin in opposite directions, which we denote it with the positive and negative. So keep that in mind as you are doing your quantum numbers. You know that you can never have the same quantum numbers. Remember, as a little review, we had Aufbau, who told us that we must put electrons on the lowest energy level before you can ever fill them on the highest energy level. Hund's rule, which was the bus seat rule, told us that electrons are going to singularly occupy an orbital before there will ever be 2 of them in that orbital. We call that the bus seat rule. And then lastly, Pauli exclusion principle tells us that electrons will never be found in the exact same location at the exact same time. They can be very close, and when they are, they have opposite spins. You can practice these problems on any element that you would like to. There are many pages in our book. You can draw your electron configuration, your orbital notation, and give your quantum numbers for any electron that you choose. If I were you, I would take some time and practice the quantum numbers, orbital notation, and electron configuration for iron. That's a little hint that you might see that one day on a little quiz, say a test at the end. Well, had a great time today talking about this. Thanks for hanging in there. If you have any questions, come see us in class. Best of luck on your test. Mr. Mullins is out.